Hello everyone, my name is Jean-Pierre Smith. I'm a PhD student at ETH Zurich, and I'm happy to have the opportunity today to talk to you about website fingerprinting in the age of QUIC, which is a paper co-authored by myself, Professor Pratik Mittal of Princeton University, and Professor Adrian Perrig of ETH Zurich. Now, originally, an adversary who is located in the network and who is interested in identifying which web page a user is visiting could do so by observing the content of the communication between the user and the web server. To counteract this, the communication was encrypted using SSL TLS, and while the content was no longer available to the adversary, he could still discern which web page was being visited by observing the destination IP address, certificates, and the server name indicator provided from the user to the web server. Privacy-conscious users therefore turn towards privacy-enhancing technologies such as VPNs and anonymity networks. However, these privacy-enhancing technologies still leak communication metadata, that is, packet sizes, timestamps, and directions, and these form the basis of network-based website fingerprinting attacks, which the adversary can still use to identify which web page is being visited. So in a network-based website fingerprinting attack, the adversary, who is located on the encrypted communication channel between the user and the entry point to the privacy-enhancing technology, observes a sequence of packet sizes, timestamps, and directions. He feeds this metadata to a feature extraction process, which extracts details such as the total transmission time or the total transmission size or distribution of packet sizes, etc. And these features are then fed to a pre-trained classifier. This classifier informs the adversary whether the metadata is associated with one of the pages he's interested in to which he's interested in detecting visits, that is one of his monitored web pages, or if it belongs to some other unmonitored web page. Now, there has been quite a bit of work in the area of network-based website fingerprinting in both attacks and defenses. However, most of this work has focused on the TCP setting. At this moment, however, the web is undergoing a transition, and that transition is from TCP to QUIC. QUIC is a UDP-based multiplex transport protocol that was first deployed by Google but has now been standardized at the IETF and is slated to be the only protocol that supports the next generation of HTTP, HTTP3. And while QUIC is similar to TCP in that it is congestion controlled and it performs reliable delivery, it differs from TCP in a number of ways. For example, in TCP, a single in-order flow control byte stream is provided from the client to the server, whereas in QUIC, multiple byte streams are sent over a single connection. And these byte streams are all individually flow controlled, and a loss on one stream does not affect the transmissions on another stream. Furthermore, in TCP, primarily only the data of the transmission was encrypted by TLS. And this allowed an adversary who is cleaning his data to perform his website fingerprinting attacks to easily remove control messages, control packets, and acknowledgements. In QUIC, however, packet numbers, acknowledgements, control messages are all encrypted alongside the data and are all variable length. And what this means is that the adversary can no longer simply discard a packet knowing for certainty that it is a control packet and not a small data packet. Furthermore, connections in QUIC are established in 0 to 2 RTTs, whereas connections in TCP are established in 1 to 3 RTTs. This means that patterns which are observed in the communication between the client and the web server may occur at different times in the connection and may be shifted forward or backward depending on which protocol is being used, and can therefore affect the adversary's approach in extracting features from the communication he witnesses. And finally, whereas originally in the internet, when an adversary observed the loading of a web page, he would know that this was solely TCP connections within that corresponded to the metadata he's observing. However, due to QUIC's backwards compatibility and future support, QUIC's backward compatibility with TCP, that is, when a browser loads a web page, it loads the HTML page, and this HTML page may load dependent resources. The HTML page may be loaded using QUIC, however, the dependent resources may still need to be loaded using TCP, as the remote servers which they are located on may not yet support QUIC. An adversary that observes metadata in the network therefore now has to account for the fact that this metadata may come from both QUIC and TCP connections within the same for the same web page load. So what we ask in this work is, given all of these changes between the TCP and QUIC protocol, how might the website fingerprinting landscape change with the introduction of QUIC? To answer this question, we use the similar procedure that the adversary uses when performing his attacks. That is, we created an setup for collecting a large data set of website fingerprinting samples on which the adversary can train his classifier. And in our setup, the adversary is located on the encrypted communication between the user and a VPN gateway. Our VPN gateway was located in New York, Frankfurt, and Bengaluru, India. And this provided for a variety of network conditions. The user was emulated using the orchestration of the Chromium browser, and the adversary would observe either the user loading a web page using TCP only, or the user loading the web page using QUIC, and potentially with dependent resources using TCP. Then, the adversary constructed, using this setup, a dataset of 100 monitored web pages. These are the web pages he's interested in identifying visits of, and 16,000 unmonitored web pages. And these he uses to train the classifier to ignore samples. Now, for the classifier itself, we use the KFP, DF, PFPC, and VARCNN classifiers, which are all modern website fingerprinting classifiers, the latter three of which are all deep learning classifiers, and therefore learn features from the raw data. This is effective in this setting where the traces belong to two different protocols, and therefore different features may need to be learned. For each of these classifiers, we measured recall, which is the fraction of the monitored samples which the adversary is able to detect, and precision, which is the fraction of those samples which the classifier claims to be monitored that are actually correctly labeled as monitored. Here we use R20 precision, as it allows us to fix the number of unmonitored visits for every monitored visit that the user does in the computation of our metric, and this better emulates our user in the real world, which would not visit monitored and unmonitored samples in the same ratio as our dataset. With this setup, the first question that we sought to answer was, do TCP trained classifiers detect QUIC visits? That is, assuming that the web has now deployed QUIC, and the web pages that the adversary, or the websites that the adversary is interested in detecting, support both QUIC and TCP, but the adversary has not yet updated his collection or his approach to incorporate the QUIC protocol, potentially because he believes it is not necessary, as it is the same web page being loaded and the protocols may not be all that different. How does the adversary actually perform in this setting? And what we found was, here the underlying transport protocol matters. Consider the VARCNN classifier. When it was able to detect TCP samples with nearly 100% precision and recall, it was only able to detect less than 4% of the QUIC samples. That means 96% of the QUIC samples were actually evading detection for this classifier. The other classifiers did not perform as significantly better, and most were unable to detect the majority of the QUIC monitored samples. Therefore, an adversary will now need to consider both protocols in his future endeavors. Perhaps this was because the QUIC is somehow more difficult to fingerprint than TCP. And this is therefore what we evaluated next. Here, we trained the classifiers on TCP-only dataset as well as on a QUIC-only dataset over the same web pages, and we evaluated the classifier's performance in these respective settings. What we found was that there really is no difference between the QUIC and TCP samples in the sense of difficulty of fingerprinting, and all classifiers were able to detect both samples from both protocols with high precision and recall. The PFPC classifier, in fact, was even able to perform better on the QUIC samples, which we attribute to there being less variety in the web servers used for QUIC at the time of running these experiments. So given that QUIC is not harder to fingerprint than TCP, and that an adversary needs to account for both protocols, how may he go about doing this? We evaluated two potential approaches for jointly classifying QUIC and TCP samples. The mixed approach, which is the direct approach, where the adversary takes a classifier and he trains it on a mixture of QUIC and TCP samples. And another approach, which leverages the fact that since the TCP-only classifier and the QUIC-only classifier are so adept at detecting detecting samples loaded with the respective protocols, if the adversary is able to distinguish whether a sample is a QUIC or a TCP sample, then he can pass it to the dedicated classifier. We'll begin with the mixed classification approach. So we evaluated all of the classifiers trained on a mixture of QUIC and TCP samples across monitored and unmonitored samples, and we found that, as expected, the additional noise added to the dataset by the second protocol reduces the classification accuracy for most, if not all, of the classifiers. The exception of which is var-CNN, which, due to having among the longest training time, as well as using two independent neural networks combined in an ensemble, was least affected by this change. And what this means for us is that if an adversary would like to continue attacking the network and account for the fact that there are now both protocols, then he needs to either increase the training time or the number of samples he uses in the training beyond what is currently used in the website fingerprinting literature. So what about this split setting? Well, can the adversary actually train an distinguisher to identify which protocol the trace is loaded with? And so we created such a distinguisher from a random forest classifier trained on a similar dataset as is used for the KFP classifier. And this distinguisher outputs a probability, PD, that the sample is a TCP sample, and 1 minus PD, that it is a QUIC sample. And we found that after only 150 samples, that's 75 QUIC and 75 TCP samples, the distinguisher was able to detect with over 99% accuracy whether the sample was first loaded with TCP or whether it was first loaded with QUIC. And when we investigated why this was the case, we found that this was due to the differences in handshakes. For example, the differences in when the connection is established, as well as in the size of the initial packets, such as the fact that QUIC uses 1200 byte packets to start its connection, whereas TCP uses its small syntax. So given that we can actually distinguish the protocols, can we now go ahead and build an ensemble? So in this ensemble, the TCP classifier is trained only on TCP samples, and the QUIC classifier is trained only on QUIC samples. The distinguisher, by contrast, is trained on both QUIC and TCP samples. When it comes to actually distinguishing between the two protocols and classifying a sample, the distinguisher outputs its prediction that the sample is a TCP sample. The TCP classifier outputs its prediction that this sample belongs to a particular web page. And the QUIC classifier also outputs its confidence that this sample belongs to a particular web page. The final prediction is the weighted sum of these two predictions with the belief of the distinguisher. Surprisingly, this split classification approach performed worse than the mixed classifier. Despite the TCP and QUIC classifiers performing very well, the result of the split classifier is not that it performs as the weighted average of these two classifiers. And the reason for this is that unlike the mixed classifier, the split ensemble, in the split ensemble, the individual TCP and QUIC classifiers only see a fraction of the samples of the two protocols. So the TCP classifier sees only the TCP, the QUIC only the QUIC, whereas the mixed classifier is able to leverage information common to these two protocols in the samples it sees. Moving forward, it is likely that the adversary would use a mixed setting or increase the data set to account for the fact that the TCP and QUIC sample classifiers would need to saturate with the number of samples they're given. So, in conclusion, the web is transitioning to QUIC, and this has privacy implications, especially in the website fingerprinting landscape. Despite QUIC classification not being inherently more difficult than TCP, if the adversary does not consider QUIC in his training procedure, QUIC traces will evade classifiers that are trained on only TCP. However, joint classification is possible of both QUIC and TCP samples. However, at a cost, the adversary will either need to increase the number of samples or train for longer. And finally, determining if a trace begins with QUIC or TCP is trivial. And this can have an impact of reducing the anonymity set in when the adversary is performing his classification. For example, if the adversary sees the web page is being loaded with QUIC, he can already rule out any TCP-only web pages from his predictions. And with this, I would like to end my presentation, and I would like to thank you for your time. The dataset and code for our work can be found at this location if you are interested, and I am open to your questions. Thank you.